Okay, perfect. Now I'm just going to share my screen. Microsoft PowerPoint. And I'm going to play from the start. And that would help if thank you. Can you guys, Kono-san, can you see my screen that I'm sharing?
Yes, I can.
Okay, perfect. Okay, so I'm going to get started here. That's one thing I don't want to have to debug right now. Okay, perfect. Okay, so when we had an initial call a couple of weeks back where we talked a bit about the plans for an ARM64 code generator in Eclipse OMR. The people that are sort of participating in this project are coming from a variety of different backgrounds in terms of experience with compiler technology in general, experience with OMR, experience with ARM, that kind of thing. And what I thought I could do is to start to level set most people on sort of the basic concepts of how a backend in OMR actually works and how the OMR compiler technology actually works. So what I thought I would do today is really sort of start from the beginning and sort of take you through a very high-level overview of the Testarossa compiler architecture that's available in OMR. It'll have a particular bent toward OpenJ9, and the reason that that's useful though is because we can talk about it in an actual context as opposed to just very high-level concepts of the compiler technology. I can actually tie it to something. So I'd like to take you through from a high level. This will be very some of you will probably find this very familiar already, so I apologize for that. But I think that as we get into this more and as we start to have a few more discussions around this technology, it's going to get a lot more deeper and a lot more relevant to you. So anyway, so let's get started here. Okay, so just to start off with a very big picture of the compiler technology as it sits in a much bigger context. So the bigger context in this particular diagram here is OpenJ9. And as you can see, the compiler technology itself is just one part of this much, much bigger picture. And the key thing here is that the compiler technology doesn't sort of sit alone. It actually does need to communicate with the virtual machine that's actually running. Regardless of whether or not this is OpenJ9 or not, it does need to communicate with the higher level virtual machine, and it does need to talk to the runtime in some way as well. So this is where you can kind of get into native code when you're talking about Java through JNI or some tooling interfaces with JVM-TI. One thing that's missing on here as well is sort of conversations that the compiler might need to have with the operating system itself, and the means that we have for going through there. And there isn't actually an arrow in this diagram. It's actually quite old, but the means that the compiler uses for that is to actually go through something called the port library. And the port library is really a layer, it's an abstract layer that sits between virtual machine technology and the underlying operating system. So regardless of the OS that we're running on, we just sort of have to code to a particular API. So that's sort of where the compiler sits in the broader context. Let me just say that I'm hoping that this kind of meeting today will be very informal, and I'm expecting you guys to interrupt me at any time to ask me any question you want. I want this to be very interactive, so I just don't want to talk for 90 minutes. By all means, speak your mind and ask any question that you might want to ask. Okay, an equally old diagram on some of the architecture within the actual the component itself. And again, this does have a bit of a Java bias to it. But the way that sort of things work within Testarossa is that you really need to sort of start off with the core technology really sort of sits with an API that talks to a particular runtime system. So in this particular case here, we've got on the left-hand side here in blue, you can actually have sort of what we've traditionally called a front-end interface to the runtime technology, and it's that front-end interface is where the compiler really asks a lot of questions about the environment in which it's running, and it expects to get answers back. So, for example, questions about the object model, or if there's sort of language-specific semantics it needs in order to do optimizations, or if there's information around debugging or tracing and that kind of stuff, it really needs to talk to these front ends. And there is sort of this generic front-end interface that different consumers of this compiler technology can go and specialize for its own use. And I mean, I've got a few examples here around, we've got ahead of time compile for Java. There's like an embedded Java there as well. We've got other technologies that are built on this that have nothing to do with Java. You can really define these as you like. And then sort of the first step in the overall, the first stage in sort of the compilation process, and it's something that every compiler is going to need to provide in some way, is what we call an IL generator. It's called IR generator here, but throughout the code, if you ever look at the code, you're going to see IL generator used quite extensively. And what the IL generator is really there to do is to take some representation of the thing that you want to compile in the representation that a particular runtime has it, and converts it into an internal representation that the Testarossa compiler technology can deal with. And the internal representation that Testarossa uses is a tree-based format, and we don't really have a great name for it. People call it trees, though, but that's kind of what it's referred to, the trees or something like that. So every sort of language runtime is going to need to provide some kind of IL generator for producing the internal representation. If you've been sort of following the OMR project as it's been evolving since the compiler technology was open sourced in September of 2016, one of the advances that we've actually provided, and something that we're very heavily invested in and putting a lot of work into improving, is something called JIT Builder. And what JIT Builder really is, it's a much more simplified interface from your language runtime to the compiler technology. So it really simplifies the process by which the process of producing an IL generator. It really sort of takes that out of the equation and allows you to map the things in your language runtime to the compiler technology much easier. So that in itself is an entire presentation that we can talk about at some point in the future. Okay, so once you get past the IL generator, we have a variety of high-level optimizations that are really based on the trees that can be performed. The compiler technology actually has a very rich suite of optimizations. They're actually fairly powerful optimizations as well. I can't remember exactly how many are actually in OMR, have been contributed to OMR, but I think between OMR and OpenJ9 there must be like 120, if not more, optimizations that can be applied. The way that the optimizations work is that they consume trees and they also produce trees as well. In the most theoretical sense, you can reorder these optimizations as you see fit. However, in practice, and this isn't necessarily the right answer, but in practice, there are dependencies between some of the optimizations such that the ordering is a certain ordering is required, and actually that's something that we're working to get rid of. Anyways, so it does a whole suite of optimizations. These are things that, like they're classical compiler optimizations, like loop optimizations. There's like data flow optimizations. There's commenting, simplification, very bread and butter kind of compiler optimizations. There are also more runtime specific sort of optimizations that are available. So things like removing checks, like array checks, for example, or if there are ways of removing synchronization, that sort of thing. There's optimizations like that. There's a bunch of speculative optimizations as well, and we have, and this technology, when coupled with OpenJ9, has the ability of doing a lot of sort of speculative optimizations, and it has compensation paths for when those conditions are no longer valid. So very powerful stuff. And then once things flow out of the optimizer, you go into one of the backends for the processor that you're attempting to target. The main code generators that we have in OMR right now are for x86 and PowerPC and System-Z and 32-bit ARM. This particular chart here shows even more SH4 and MIPS. We used to have a deeper set of backends that were available, but at the moment in OMR, it's just the 4. And in terms of what we're talking about here, we're talking about supplementing the ARM code generator with 64-bit capabilities as well. So, and based on our sort of earlier discussions about this, it's looking like it might be a new code generator on its own. But the code generator is basically responsible for taking trees and producing instructions from them, and these instructions can be executed. So that's really the path that it follows. Now, that's sort of the core flow through the compiler. There are other components as well that may be consulted for information as the compilation proceeds. So, for example, some optimizations do rely on profiling information, or they will perform much better in the context of profiling information. So there is interaction with the profile manager to get data about a particular about a particular opcode or a particular bytecode, and if there's something that we can specialize better from that. It also interacts with the runtime in terms of like when the code is being produced, and needing to call certain methods at runtime from compiled code, that sort of thing. So when we're looking at just OMR, though, you usually don't really deal with the profiler right now. We're not really going to be dealing with the runtime right now. I think most of the work of this particular work group is going to be spent looking at just the code generator aspect of this. But this is really to give you a higher level overview. Okay. So what I thought I would do is to start going through a fairly simple example of how a method actually gets compiled in Java, in using OpenJ9 as an example. I think it's really going to touch on a lot of the concepts here. So given some virtual machine, I'm going to assume it's Java, what you sort of start off with is Java bytecodes. And normally your virtual machine is just simply going to interpret those bytecodes. So what we're really talking about here with this compiler technology is how do we take those bytecodes and actually compile them at runtime into native instructions, into binary code that can actually be executed. So as I talked about before in terms of the architecture, the way that this works is that we have a means by which the compiler can take Java bytecodes, and through the IL generator, it can produce the Testarossa trees for consumption within Testarossa. So that's what the ILGen does. And then it calls those trees flow into the optimizer. Depending on the strategy in which you want to compile those methods, you can throw different packages of these optimizations at those trees to get them to do different things. It's a very kind of iterative process as well. So you can pass these trees through a variety of different optimizations over and over again. And when that's done, these trees flow into the code generator. and a process known as tree evaluation occurs, which basically takes those trees, Testarossa IL trees, and turns them into an instruction stream, a flat instruction stream that's really based on, that really uses sort of an infinite virtual register set. And then we go through a very platform-specific register assignment phase where we actually take those virtual pseudo-registers and map them into real machine registers. And then you end up going through a binary encoding phase, which really does a lot of the sort of last-minute things where you actually take that and map it into a buffer that's executable. And you pass that compiled method back to the virtual machine and say, go, please execute it. So that's really the process at a very high level. So I think what I'd like to do is to drill down deeper into each one of these different phases and talk a bit more about how it does the things that it actually does. So the first step is IL generator, which is sort of colloquially called IllGen. So in general, Java bytecodes are not really great for analysis, and it's not something that's easily consumed or worked on within the compiler technology. So what we end up doing is we turn those bytecodes into an internal representation that we know is easy to work with, and for which the properties of that IL are reasonably understood, and it can be used by multiple language front ends as well. So what we end up doing is producing these trees, and the IllGen phase itself is actually just an abstract interpreter. So it really walks through the bytecodes just like the Java interpreter would, and it's basically interpreting what it comes across here. So as an example, when we hit the first iLoad bytecode here, we end up creating what's called a node in our tree, and a node is really just a representation of a particular expression. So we produce an iLoad node. We go on to the next bytecode. We produce yet another iLoad node. We come across a third bytecode that is going to be consuming the previous two bytecodes as its operands. And the way that we handle that is that we create a third node to represent the add expression, and then the way that we associate the operands with this particular expression is by making the first two nodes children of the add node. So that's what those little arrows are intending to represent there. We carry on. We come to a store node that is going to be consuming that takes as its operand the add. So we create a node for that, and we make that association. And what we're starting to see here is sort of a complete expression, or is like a complete statement being formed here. So in this particular case, this is really the representation of adding B to A, and then storing the result of that back into A. And after each of these statements really is internally within Testarossa, what we refer to those as is a treetop, and we actually create a special kind of node called the treetop that sort of points to the root of one of these statements. And I think informally what a treetop is really supposed to represent is an expression that's got a single side effect with it. So in this case, the major side effect here is going to be the store into A. So that alone should get its own treetop. You would never find a treetop that actually has you would never associate a tree with a treetop that's got more than one side effect. So for example, it has two stores in it, or it has two calls in it, for example, or a call and a store, that sort of thing. It would always need to have a single side effect associated with it. And that's going to make our understanding of these trees by optimizations and other parts of the compiler a lot easier to reason about in the future. So we carry on, and we get to the next statement, and we end up producing yet another treetop for the next set of bytecodes there. And what we do when we're producing all these treetops is we actually link them all together in program order. So at the end of consuming all the bytecodes for a particular method, we're going to end up having a sort of a very long linked list of these treetops, as we see here in the next step. Now, this is one long linear list, but in reality, a lot of methods actually do have some form of control flow in them. And the way that happens is that we can introduce branching into these treetops, and the means by which we do that is we actually do have special treetops to represent where the target of a branch is going to be, and special IL nodes that actually represent like conditional branches or unconditional branches and that sort of thing. So what we tend to do with these treetops is we actually start to group them into what we call basic blocks. And these are single entry, single exit blocks. And there are special nodes that get created to delimit the beginning of a block, the basic block start, and there's a special node that indicates the basic block end. And we can go through and produce these basic blocks from these treetops. And basically link them together. Just going through these. So the basic blocks and then the edges that go between them basically form the control flow graph. And then if you take the control flow graph and look at the underlying trees in each of these blocks, that's really what forms the intermediate language that Testarossa is going to be consuming in a lot of its optimizations and in the back end. So what I just said here, it was a Java example, but any language runtime that wants to produce, that wants to use this architecture is going to have to end up producing trees at some point. And sort of the same rules around treetops and the same rules around how edges are formed between blocks and the semantics of basic blocks all have to apply across those different languages. Okay. So once we have produced the initial set of internal intermediate language for a particular, let's say, a set of bytecodes, we can pass that into the optimizer, a high-level optimizer. And like I said before, there's probably at least 120 optimizations that are available. It would be absolutely impossible to go through each and every one of those. And it's certainly possible to drill down into those. If anybody has any sort of specific interest, we can do that at another time. We can bring in the right people that understand each of those optimizations to talk about them. But it is, suffice it to say, it does consume a fairly large part of the compiler technology. And I'm just going to give a very quick overview of what it can do, just to give you a taste of sort of the optimizations that it's capable of and how it actually goes about manipulating certain trees. But basically, the optimizer consists of a variety of different optimizations that are each controlled by their own optimization manager. And basically, an optimization behaves in more or less in two phases, right? It basically does an analysis of what work is possible, what work is needed to be done, and so it's looking for opportunities. And it looks to make sure that any sort of transformation that it might want to do is done correctly and it's done safely as well. So once it's done that analysis, it then goes through and does the actual transformation that actually manipulates trees. So the analysis phase doesn't actually change any of the trees, anything like that, because it can bail out at any moment. But once it's proven that that there is an opportunity, it's worthwhile doing this change, and that it can be done correctly, then it'll go and transform the trees. And hopefully, we're better off from that. Or we're uncovering we may not be necessarily better off immediately, but what it might do is to expose opportunities for further optimizations that are going to be coming up. Okay, so just a quick example of some of the things that we can do. So if we look at a couple of treetops in order, one of the things that can get done is a strength reduction optimization. So basically, by analyzing this code, we can figure out that we can replace the multiply with a shift instruction. So let's go ahead and do that. And then a very, very, very frequent optimization that occurs in this code is something called commoning, and it's really like a common subexpression elimination, optimization. So what that means here in the context of these trees is that we can see that we've got two integer loads of some variable, and we don't necessarily need to do this thing twice, right? We only really need to perform this operation once. So what we can do is assume that the operation is going to occur by the first tree, and then we simply just say that we can just common up what we call commoning up the operation under the subtract node there. So basically, that operation doesn't need to be repeated. We already know that we've done that. There's other rules around how this can actually happen, but from this very simple example, we're just performing that straight up. The resulting trees in this case are very likely going to be a DAG. We don't allow cycles in any of the trees that we do form. I guess I should have mentioned that earlier. So another optimization that we can do is something called copy propagation. So looking at this, sort of the next set of optimizations that we can apply here, we are producing the result of some expression and storing it into a variable A, and then the next treetop is coming along and actually loading that A. And what we can basically see is that instead of loading that A for memory, what we can actually do is to just basically replace it with the result of the IAD, right? It's fairly straightforward copy propagation there. And then we can use like a simplification optimization as well, which kind of looks to see if there's unnecessary trees or operations that we can sort of fold into as small unit as possible. So in this particular case, we look at we're doing like the text on the right says, we're doing A. It's seen the pattern A plus B minus B, and it knows I can simply replace that with just an A. So getting rid of the B minus B, and that's what this is doing. The next thing that it can look at is, okay, well, I've got a store to some variable followed by another store to that variable. It's a local, so I know that the first store, or the second store is really going to subsume the first one, so I don't really need to do the store at all in the first case, because the second one's just going to overwrite it. So I simply replace that with a treetop. And then we have another phase called dead trees elimination that can actually go ahead and remove dead treetops. So all in all, what's going to end up happening is that this tree is actually, oops, sorry about that. Oops. We're going to simplify this down to as a small a unit as possible, and we can keep going and going and going, applying as many optimizations as possible. Oftentimes, when you apply optimization, it actually uncovers opportunities for other optimizations, and then we sort of iterate on that. The optimizer is a fairly big topic, so and it's not really the focus of what we wanted to talk about with this work group, but if there's ever any interest in anything in particular there, we can certainly give a much deeper dive into that. So, right. So where we go next is into the code generator and through a phase that we call tree evaluation. Just a quick thought about the code generator. So ultimately, its role is really to produce binary code from IL. That's a lot of steps happen between IL being introduced and when the binary code is actually produced. And what we do is we've actually broken up the code generator into a variety of different phases that can be customized by a particular language runtime or the architecture that you're running on. So on the far left here, I just happen to list all the phases that are available in the current OMR compiler. Not every runtime is actually going to use these, or not every architecture is even going to use these. You just sort of pick and choose from these different phases. In the middle column, I've got an example of how a particular architecture can provide their own phases that make sense to that particular architecture. And on the far right is sort of an example of a package of phases that that a particular runtime could actually do. And in fact, this particular package here is the sort of the default one that an OMR code generator would use unless it was actually overridden by something by a project downstream. This is sort of the default ordering of the phases. And one of these phases, the first phase is tree evaluation, and it's really the thing that's going to be taking the IL trees and turning them into sort of this flat instruction form that can be taken further into the code generation process. So the word that gets used a lot around here is evaluation, and the sort of the act of inspecting an IL node and then turning it into an instruction is called an evaluation. And like the quote there says, it's to generate instructions which, when executed, will cause the tree's value to appear in some virtual register. So the result of evaluating a node is to produce a sequence of sort of virtual instructions that will use, whose result will be a virtual register that represents the value of that particular tree. We'll see that in just a sec. The virtual registers that are used come from an infinite set, so you can use as many virtual registers as you need in order to accomplish the thing that you want. You don't have to worry about limitations of your particular architecture that you're targeting. In this particular phase, you use an infinite set of registers. Sorry, I'm just reading that bullet point there. If a node produces a result consumed by other nodes, the net result of the evaluation is a virtual register that represents a result. Yeah, so that's basically what I just said. I was just reading that to make sure that was the case. So basically some rules around evaluating nodes. So this is really done in a post-order traversal fashion. So the children of a node are always evaluated before an actual node itself. So you always go from the bottom up. If, as a result of evaluating a node, it produces the result in a register, that node must set what we call setting that register on the node itself. So you're basically associating that virtual register with that particular node. If we ever get into the code, and we will later, I don't mean today, but if we ever get into the code, you're going to see that happen a lot. You're going to see that setting of the register on the node a lot. One thing that it does that really guides the whole process here and tries to make the code generation as efficient as possible is by looking at the reference counts. And by reference count, this really means is how many instances of a node are really seen in a particular program. And it can, we can use that information to make decisions about, is this the first use, is this the last use of a node, that kind of thing. And we can make decisions about like when registers die, when registers will go live, that kind of thing. So yeah, that's what it says there. We can make reuse decisions based on, if the reference count goes to 1, you know that this is going to be the last reference you see of this node in this method. And an evaluator does not usually decrement its own reference count. The parent is responsible for decrementing the reference count on a particular node. So, okay, so an example here. Fairly simple tree representing that statement there. So the way that this works is that we do we need to have some kind of a pointer to the instruction stream that we're working on. So this is the stream of virtual instructions, I guess you can call it that. And the way that this works is we basically do a post-order traversal like we're talking here. We evaluate the children before the parent. So we get to the bottom here, there's no more children to traverse, so now we actually have to do something here. So what we're going to do here is actually what we call evaluating this node. And again, we're assuming an infinite supply of registers. So what this really turns into, and this is, it's basically a load. So I'm just going to use a very machine generic kind of pseudo assembly here. This isn't any particular architecture or anything like that. But what it's really doing here is loading the contents of A into some virtual register that we happen to call R203. So the evaluation of a load results in that particular virtual instruction. And since the result of that is stored into 203, into register 203, we can actually set register 203 on that node. So anytime in the future you look at that node, you can ask, has a virtual register been assigned to you yet? And if the answer is yes, you know you've actually evaluated that node in the past, and you can just use the value that's stored in that virtual register. But if it hasn't, then this is really the first time that we actually have to assign that here. So that's the first opportunity for it. So anyways, we do that. We go to the next child, and we basically go through the same process of evaluation. In this case, it's loading B into register 204. And again, what it does is it replaces, it sets register 204 on that node. And since we're out of children for this particular node, we now go back up to the parent, the add. And so what the add is now going to be able to do is to, since both of its children have now been evaluated, it basically replaces, it does the operation that it's supposed to be doing. So it's inserting an add instruction that stores its result into a virtual, let's say in this case 205, of its two children that have been evaluated. So we just did 203 and 204. And then we keep going here, right? So we now get up to the IML. The IML hasn't evaluated its subtract child yet, so that's what we're doing here. The subtract itself, you can see by the arrows here that the children of the subtract are already 203 and 204. We don't have to reevaluate those nodes because they've already been evaluated into a virtual. So the subtract node simply just takes its children from R203 and R204. And it needs to store it into a new register, 206. And we carry on up the tree. Same thing for the multiply. We've done 205, we've done 206. We need to put the result of that into a new one, 207. And then eventually what happens is that R207 value is stored into variable A. And we can carry on down for the rest of the rest of the instructions in this method. So if you happen to look at so there is a lot of tracing and logging information that can come out of the compiler. This is sort of a composite of different parts of that log that you can end up producing, just to make it fit onto the slide here. But what this is really showing you here is before you evaluate, it's showing you one particular treetop and the nodes underneath it. What it looks like before tree evaluation, what it looks like after we've gone through and just did the process that we just did, and what the actual underlying instructions look like. So how you can read this is that the column on the left that starts with an N, every node has got a unique ID associated with it. And N238N, for example, there is really just a sort of a convenience way of writing it for someone who's debugging some code here. It's just how we refer to that particular node. We can generate actual addresses of those node data structures, but it makes these logs look very, very busy, and in often cases they're harder to read. So we do use sort of the simplified form here. The next column over is the reference count. So in this particular case, you see that if I compare less than node as a reference count of 0, that's good because it's a treetop, and treetops should not actually be commoned. And then underneath that, you see like it's got an iLoad with a reference count of 4, which means that there's this use of that iLoad, but then there's 3 other places that actually are referencing this particular iLoad, so it's been commoned 3 times. And then we've got another iLoad and then an A-load underneath that with their own reference counts. What you can see is that after we've done a tree evaluation, the reference counts on these nodes actually get decremented. So after we've gone through this, the iLoad actually has its reference counts decremented from 4 to 3. iLoad goes down to 0, and then the iLoad goes down to the A-load goes down to 1. And that's sort of the natural result of this. And then the result of these evaluations is a virtual register, and after we've done tree evaluation, we can now report which register has been set on each of these nodes. So in the case of the iLoad, we know that was evaluated into GPR 64, so we can actually now report that when we print these in the logs. And then a little bit later, you can actually look at the virtual instructions that have been produced as a result of evaluating those trees. And indeed, they are, a very flat. It is a flat instruction representation here. The column on the left here actually refers to the instruction address. I think there might be a way of actually producing a simplified version of that, but in a lot of cases, having the actual instruction address is useful to see. But anyways, yeah. So this is a very high-level way of representing these these instructions at this point. Okay, so up until this point, we've been dealing with virtual registers, and the problem is that when you actually do want to generate this for a real machine, like x86, like ARM, whatever, that real hardware doesn't have an unlimited set of registers. And it makes it very handy during evaluation to assume that it has an unlimited number of registers, but at some point we have to make everything fit within the constraints of the target architecture. So what we do is we go through a register assignment phase, often abbreviated as RA, and what we basically do there is we map all these virtual registers to a real machine register. And the way that this particular process works is it does it through a backward pass, so it goes through all the instructions in reverse, and does that mapping. We deal with it goes one block at a time. We call this a local register assignment for that reason, because we only deal with a single basic block at a time. And the other thing about that's important about this kind of a register assignment technique is that it doesn't really know anything about control flow. So, which is why it can't really cross block boundaries, right? So, if it comes across some kind of control flow, it doesn't really know that. It can't track register state in different branches of this control flow. It really is only assuming that it's going to be one straight line piece of code. We use a mechanism called register dependencies to specify when a particular real register must be assigned to a particular virtual register. And this is used for handling calling conventions, like if the first and second parameter of a call have to be in a certain real register as the linkage specifies, or if there's a particular machine instruction that happens to have a requirement that one of its operands be in a particular machine register, like for example a shift instruction that register 3 must contain the shift count as the ISA specifies. So we use register dependencies for that. But perhaps you've already discovered that one of the real problems here is that trying to map an infinite set of registers onto a much more finite set of registers won't always succeed. So what we end up having to do is is the spill registers, what's called spilling registers. When spilling registers to memory, using memory to back up when we don't have enough registers, and then having some kind of a management code to be able to determine when something's in spill state and when it's not. So using memory to back up our register assigner allows us to assign these smaller number of registers, allows us to map the infinite set onto a smaller set. The register assigner has to obey the register dependencies as well. And in the case of Java, we have to use, it also has another duty in building these register maps, because it understands what's in what we call a collected register or not. I'm not going to talk really much about that right now, but it does have other tasks that it must perform during register assignment. So just a quick example on how this actually works. So if you have a stream of instructions like this that's using virtual registers, let's assume for this moment that we have 3 real registers in this particular architecture. They're just called X, Y, and Z. And at this particular point in the register assignment, we're actually walking backwards. As I said, that this technology works. We've already gone through and assigned stuff to R203 and R204. So in this particular case, let's assume that they've already been assigned to real register X and real register Y for 204. So the way that this will work is that we get to this particular instruction, and we see that there's one register that's needing to be assigned here. It's 207. And the question is there a register available for it? And the answer is yes, because register Z is still available. So we can give it register Z. And we're happy, so we go on to the next instruction. So here, this is an example of an instruction that has a destination, like a target, or a definition, and it's also got registers that it's actually using. So the way that that this works is that we actually process the definitions first. So the first register that we're looking to assign is for 207. So, and it turns out we've already got a register assigned to it, so Z, so that's great. But the thing to notice here is that register 207 is no longer used. If you keep looking up in the app in the program, this is the last use of register 207. So after this point, it doesn't need to hang on to the assignment for register Z. So after it's done this assignment, it basically says, I'm done with register Z. Somebody else can use it. So it'll basically free it up for someone else to use it. It's a definition, so this is going to be the first def point here. So then the register assignment proceeds on to R205 and R206. So neither of those have got registers assigned to them yet. So let's start with 206. Z is available now, so let's use register Z. And we now move on to 205. But the problem that we have here is that X, Y, and Z are our entire register set is actually used. So we don't actually have a free real register to assign to 205. So what we end up having to do is to use the spilling mechanism to make this work. And the way that works is we say, okay, let's pick a register. And most backends have got some heuristics to figure out what the best register is to spill. But in this particular case, we chose X. That's the register that we want. So, but because it was already being used, what we have to end up doing here is insert a load from some spill slot into register X, because all the code beneath us had already assumed that that value was in real register X. So what we're actually inserting here is a load from some spill location, which we haven't stored into yet. So we now say that R203, which had X, is in a spill state. R205 is now given the real register X, and we're happy. So let's carry on. We're now at subtract instruction, so we process the definition first. So let's just go back for a sec. So R206 was already assigned to Z, and R204 was already in Y. But R203 here is a bit of a challenge because it's in a spill state. So it actually isn't sitting in a register right now. So we're going to have to find a register for that. And what we end up choosing is, so the other thing I wanted to point out here, let me just go back here. So R206 here is actually the first use of it. So it actually dies after this point. So after we've assigned Z in this case, it's available for assignment. So in this particular case, R203, which we're looking for a register, is going to get register Z. But since R203 was in a spill state, we actually have to insert a store of Z into that spill slot, because a little bit later on we're going to reload it back into X. So this is where that symmetric spilling is coming into play here. So we have to store Z into the spill slot, and we can carry on with our register assignment. In this particular case, in this add instruction, 203, 204, 205, they're all available, so we can assign those straight away. And we just keep going, repeating the process that we've been going through here. So this particular example, really demonstrated a lot of the, well, in a very whirlwind way, it really demonstrated a lot of the sort of the things that a register assigner has to deal with. And I guess that's it for register assignment, yeah. All right, so I can pause there if there happen to be any questions on that, because I did go through that fairly quickly.
Daryl, can I ask one question?
Absolutely.
I guess the register assignment process is mostly platform independent, but except for the kind of registers or number of those registers, but do you see any CPU dependent thing about register assignment? Any characteristics or?
Yeah, I think you're right that I would say at least 90% of the DNA in the register assigners are the same. I think we have had some discussions in the past about commenting up a lot of the functionality between the different architectures, because they are basically behaving the same way. There are some architectural differences that do come into play with regards to the way that if there's sort of in special like implied registers that happen to be used within certain instructions and certain architectures, or if there's special ways of choosing a register, like I can use the upper half of a word or that kind of thing. So, but even having said all that, I think that a lot of that could be abstracted away, and we could actually do a much more general job of doing this. Now, having said that, though, it's going to be a big task, because a lot of these registers, each of these backends has invested quite a bit in their own implementation of these, even though they are basically doing the same thing. So re-implementing this in a generic way is going to be a tedious task, but it's and perhaps an error-prone task as well. So we have to be super careful about doing that. But yeah, you're right that there are very few examples of where this actually is a where platform specifics are required.
Okay, thanks.
Okay. So there's just one last little phase that we have to go through when we're producing code. And it's really where we take those assigned instructions and actually write them out into a buffer. In terms of the compiler technology here, we call that a code cache. And so we go through this phase called binary encoding, and this is very architecture specific. So for each of those virtual instructions, depending on what opcode that actually is in use, it actually produces the binary representation of that instruction with the registers encoded, with the memory references encoded, all that sort of thing. It's also responsible for writing out the prologues and the epilogues in this particular function. It does relocation processing. So for example, handling if you've got branches within a method, it needs to be able to figure out like the branch displacements and that kind of thing. In the case of Java, it has to handle the ahead of time compile relocations, that kind of thing. And it also handles things called snippets, which are really small out-of-line sections of code that may be needed in some exceptional cases for some opcodes. But yeah, I mean, but that's basically it. I mean, once we've done that, we've got all the code written into a buffer, and that code can actually be handed back to the VM for execution or whatever it wishes to do with it. So that's really the whirlwind tour of the compiler technology. I really just assumed this was going to be the start of a lot of the discussions that we were going to have on this. This was just to give everybody sort of a flavor of what's possible, with a bit more focus on the code generator, which is what people are really going to be interested in here. I expect that looking forward, the kinds of things that I'd like to talk about next, I don't want to do that today. I want to do that, maybe schedule something next week when more people are available, to start talking about the conceptual integrity around some of these different components. So things like, what does the machine class do in the code generator? What is the code generator class supposed to do? What is a register? What is an instruction? How do register dependencies work? What kinds of things do we actually have to architect for AArch64? So for example, how do we represent the instructions and their properties? How do we fill out the machine class? How do we design the evaluators, that kind of thing, right? So start to have those kinds of discussions. But hopefully this is just to give everybody a flavor of what's there. But I think I've maybe talked enough. I'd like to open it up for any questions that anybody might have on anything here. So. No? No questions? Okay. Well. Okay, if there aren't any questions, I think the next steps here, I'd like to, convene another call, perhaps on Monday evening Eastern time, to maybe start talking through some of the other components of the code generator in a little bit more detail. Like I said before, things like the machine class and the linkage class and the code generator class and that sort of thing. I'd also like to talk a little bit about how the code itself is structured in the code generator. And if you look at the compiler technology, it actually uses something that we call extensible classes. It's a way of architecting the classes to make them extensible. And I'd like to, if you've never actually seen that kind of code before, it may strike you as a bit odd. There are good reasons for doing what we did, and I'd like to explain those. Hopefully not try to overly justify them, but try to explain what it's actually trying to accomplish and how you architect a class that uses extensible class in that format. So I think I'd like to talk about that next. Actually, that might be a good thing to talk about, extensible classes. So So what I'm going to do is to schedule something on Monday. Kono-san, it'll be, I guess, very early Tuesday for you again.
No problem.
And pardon me?
No problem.
Okay, awesome. Okay, so are there any other, if there are no other questions, then I think I'll just conclude the call right now, and we'll pick this up on Monday when we have a little bit more, a few more participants. Okay? All right, thanks everyone.
Thank you very much.